In our previous investigation, we discovered why AI chips became the world's most valuable resource. But chips alone don't create artificial intelligence. They don't answer your questions. They don't generate images. They don't train trillion-parameter models. They need something much larger, a hidden physical world made of data centers, fiber optic networks, cooling systems, and enormous amounts of electricity. Today, we're going inside that invisible infrastructure to answer one question: where does AI actually live? The answer will take us inside windowless buildings that consume more electricity than entire cities. Along cables at the bottom of the ocean, thinner than a garden hose, carrying almost every word humanity sends across the sea. Into cooling systems that move enough liquid to fill swimming pools every few minutes. And to the gates of nuclear power plants, being switched back on for a single customer. Because here's what almost nobody realizes. Every time you type a question into an AI chatbot, you are reaching into a physical machine. A machine spread across continents. A machine that hums and heats and drinks power on a scale we usually reserve for nations. Welcome back to Hidden Value. Ask most people where AI lives, and they'll give you the same answer. The cloud. It's a beautiful word, soft, weightless, somewhere overhead. The name suggests that your photos, your messages, your AI conversations exist as pure information, floating free of the physical world. It is also, perhaps, the most successful piece of misdirection in the history of technology. Because there is no cloud. There has never been a cloud. There are only buildings. Enormous, anonymous, heavily guarded buildings, filled with computers that belong to someone else. The word cloud actually comes from old network diagrams. When engineers drew the internet, they didn't want to draw every router and cable in the middle, so they drew a fluffy cloud symbol instead, meaning details omitted. The metaphor stuck, and for 30 years, we've been living inside that omission. Think about that. The single most important machine of the 21st century. And our mental image of it is a drawing that literally means, don't look here. Today, we're going to look. And the best way to see what's really there is to follow a single question. Yours, from the moment you press enter to the moment an answer appears. Because that journey, which feels instant, is one of the most remarkable physical trips on Earth. Type a question into an AI assistant. Press enter. What happens next? Your words are converted into electrical pulses inside your phone and handed to the nearest cell tower or Wi-Fi router. Within a few milliseconds, they leave your neighborhood, not as radio waves, but as flashes of laser light, racing through a strand of glass thinner than a human hair. That strand is fiber optic cable, and it is the circulatory system of the modern world. The light inside it travels at roughly 200,000 kilometers per second, about 2/3 the speed of light in a vacuum, slowed slightly by the glass itself. Your question hops between routers, buildings full of switching equipment at internet exchange points, and is directed toward its destination, a data center, quite possibly hundreds or even thousands of kilometers away, where the AI model is waiting. If you're in Europe asking a question to a model hosted in America, your words physically cross the Atlantic Ocean, along a cable lying on the seafloor, past shipwrecks and undersea mountains, 4 kilometers down in places. At the data center, your question is decrypted and routed to a rack of specialized servers. There, the AI chips we met in Episode 1 finally go to work, performing trillions of calculations to predict, word by word, the answer you're waiting for. Then that answer makes the entire journey back, across the ocean floor, through the exchange points, down the fiber, to your screen. Round trip, often less than a second, a physical journey that can span half the planet, completed before you finished reaching for your coffee. But that raises the obvious question: what exactly is waiting at the other end? What does the home of an artificial intelligence actually look like? From the outside, an AI data center is almost aggressively boring. A gray or beige box, the size of several football fields, ringed by fencing and cameras. No windows, no sign explaining what it is. If you drove past one, you wouldn't look twice. That's deliberate. These buildings don't want to be noticed. Yet a single large data center campus can cost more to build than a skyscraper, an airport terminal, or a sports stadium. And by 2025, the biggest AI campuses under construction were measured not in millions of dollars, but in tens of billions. There are estimated to be over 11,000 data centers in the world. The greatest concentration on Earth sits in Northern Virginia, a stretch of suburbs nicknamed Data Center Alley, where a huge share of the world's internet traffic passes through unremarkable office parks between housing developments and shopping centers. Step inside one, past the badge readers, the man-trap doors, the biometric scanners, and the boredom ends. The first thing that hits you is the sound. A constant full-body roar of fans and moving air, loud enough that workers in some halls wear hearing protection. The second thing is the wind. Cold air blasting up through floor panels or wall vents, because everything in this building is at war with heat. And then you see them. Aisle after aisle after aisle of black steel cabinets, stretching away under white light like a server-farmed cathedral. Each cabinet is called a rack, and each rack is worth more than a house. To understand why, we need to open one up. A rack is a steel cabinet about the height of a refrigerator, and it is the basic unit of the AI world. Inside are pizza box-shaped computers called servers, stacked like drawers. In an AI data center, each server carries several GPUs, the accelerator chips from Episode 1, plus conventional processors, memory, and network cards. Here's the number that matters. A traditional data center rack, the kind that hosts websites and email, draws maybe 5 to 10 kilowatts of power. A modern AI rack packed with the latest GPUs can draw well over 100 kilowatts. One cabinet, pulling as much power as dozens of homes. But a single rack on its own is not intelligent. The secret of an AI supercomputer is that thousands of GPUs must work together as one machine. And that means they have to talk to each other constantly, at staggering speed. So behind the racks lives a second hidden network, not the internet, something far faster. Ultra-high-speed interconnects link every GPU to every other GPU through dedicated switches, carrying data at speeds hundreds of times faster than your home connection. Per cable. A single AI supercomputer can contain thousands of kilometers of copper and fiber cabling woven through the racks with surgical precision. Miswire a handful of them, and a 100,000 GPU machine can stumble. Add vast banks of storage holding the training data, the text, images, and code the models learn from, and you have the anatomy of an AI factory. Compute, networking, storage, repeated tens of thousands of times in perfect rows. There's just one problem. Every one of those watts flowing into every one of those racks obeys the oldest law in physics. Energy doesn't disappear, it becomes heat. And heat, it turns out, is the monster this entire industry is fighting. Here is the uncomfortable truth about computation. Almost every joule of electricity that enters a chip leaves it as heat. A 100 kilowatt rack is, thermodynamically speaking, a 100 kilowatt space heater. Now put thousands of them in one room. Without cooling, a modern AI hall would overheat in minutes. Chips throttle, then fail. So data centers have always been, in a sense, refrigerators that happen to compute. Historically, cooling and airflow could consume a third or more of a facility's entire power budget. For decades, air was enough. Cold air in the front of the rack, hot air out the back, into sealed hot aisles that can reach temperatures you couldn't work in for long. But AI chips broke air cooling. When a single rack exceeds 100 kilowatts, you physically cannot blow enough air through it. Air is simply too thin a substance to carry the heat away fast enough. So the industry turned to something 4,000 times better at absorbing heat per unit volume. Water. Modern AI data centers run liquid directly to the chips. Cold plates, metal blocks laced with microscopic channels, sit flush against each GPU with coolant flowing through them. The warmed liquid is piped away, cooled, and returned in an endless loop. The most extreme systems go further, submerging entire servers in tanks of special non-conductive fluid, like circuit boards in an aquarium. The scale is hard to picture. A single large campus can circulate millions of liters of coolant, and facilities that use evaporative cooling can consume millions of liters of water on a hot day, which is why data centers increasingly publish water budgets like factories, and why some communities have begun asking hard questions about who gets the water. Heat is only half the equation, though, because before a data center can turn electricity into heat, it has to get the electricity. And that has become one of the biggest stories in the global economy. Let's start with a small number. One AI chatbot query. By recent estimates, answering a single question with a large AI model consumes several times more electricity than a traditional web search. On its own, a rounding error, fractions of a watt-hour. But AI models now serve billions of requests every single day, and that's just inference, using the model. Training 1 is far hungrier. A frontier training run can hold tens of thousands of GPUs at full power, continuously, for months. Add it up, and the numbers stop being cute. According to the International Energy Agency, the world's data centers consumed roughly 415 terawatt-hours of electricity in 2024. About 1.5% of all electricity on Earth, comparable to the annual consumption of a country like the United Kingdom. And the IEA projects that figure could more than double by 2030, with AI as the single biggest driver. Individual sites are growing to match. A decade ago, a big data center drew perhaps 30 megawatts. Today, AI campuses are planned in gigawatts, 1,000 megawatts or more. 1 gigawatt is roughly the output of a full-scale nuclear reactor, feeding a single campus of computers. In parts of the United States, data centers already account for a quarter of all electricity used in the state. Utilities that spent 20 years planning for flat demand are suddenly fielding requests for connections the size of cities. In some regions, the waiting list for grid power now stretches years into the future, which has pushed the AI industry to a conclusion that would have sounded absurd a decade ago. If the grid can't power the machine, build your own power. In September 2024, Microsoft signed a deal that made headlines around the world. Constellation Energy would restart a reactor at 3 Mile Island, the Pennsylvania plant, famous for America's most serious nuclear accident in 1979, and sell Microsoft its entire output, over 800 megawatts, for 20 years. A mothballed nuclear plant brought back from the dead to power artificial intelligence. And Microsoft wasn't alone. Google signed agreements for a fleet of small modular reactors, compact factory-built nuclear plants. Amazon backed SMR projects and bought a data center campus sitting directly beside an existing nuclear station. Meta signed a 20-year deal for nuclear power in Illinois. Within 18 months, the world's biggest technology companies had quietly become some of the world's biggest customers and investors in nuclear energy. It doesn't stop at nuclear. Solar farms the size of small towns are being built with data centers as their anchor customer. Wind contracts, grid-scale batteries, gas turbines installed on site, behind the meter, so a campus can run even before its grid connection exists. Some AI companies have started building data centers next to power plants, moving the computer to the electricity, because moving the electricity had become the harder problem. Follow the money and the pattern is unmistakable. The companies building AI have concluded that electricity, not chips, not talent, not data, is now the binding constraint on artificial intelligence. In Episode 1, we watched nations fight over silicon. The next fight is over watts. But power and cooling only make a data center run. They don't connect it to you. For that, we need to leave the building entirely and go to the bottom of the ocean. Here is a fact that surprises almost everyone. Your data does not cross oceans by satellite. More than 95% of all intercontinental internet traffic, every video call, every bank transfer, every AI conversation, travels through cables lying on the seafloor. There are well over 1 million kilometers of these submarine cables in service around the world, enough to wrap around the equator dozens of times. And each one is shockingly modest in person, about the diameter of a garden hose. Strip away the steel armor and waterproofing, and at the center you find a handful of glass fibers, each thinner than a human hair. Through those fibers, pulses of laser light carry staggering amounts of information. A single modern transatlantic cable can move hundreds of terabits per second, enough capacity to stream millions of high-definition videos simultaneously, through an object you could hold in one hand. Laying them is one of the most painstaking jobs in engineering. Specialized ships pay the cable out over weeks, following routes surveyed to avoid undersea cliffs, fishing zones, and earthquake faults. Near shore, robots bury it beneath the seabed to protect it from anchors and trawlers. When a cable breaks, and they do, over 100 times a year, mostly from fishing gear and anchors, a repair ship must sail out, hook the cable off the bottom, haul it up, and splice glass fibers together. On the deck of a moving ship. On land, the network continues. Millions of kilometers of buried fiber connecting cities and carrier hotels, buildings where hundreds of networks physically meet and the internet's handshakes actually happen. This is the nervous system of artificial intelligence, and its performance is measured in a currency most people never think about: time. There is one problem in this entire system that no amount of money can solve: the speed of light. Light in fiber covers about 200 kilometers every millisecond. That sounds infinite. It isn't. New York to London and back, the bare physics, before a single computer touches your data, takes about 55 milliseconds. Add routing, switching, and processing, and real-world delays stack up fast. Engineers call this latency, and humans are astonishingly sensitive to it. Delays under about 100 milliseconds feel instant. A few hundred, and a conversation with an AI voice assistant starts to feel wrong. The pauses stretch. The illusion of talking to something breaks. This is why the map of AI infrastructure looks the way it does. You cannot serve the world from one giant data center. Physics won't allow it. So providers copy their models to data centers on every continent and route each user to the nearest one. It's why financial firms pay fortunes to shave single milliseconds off cable routes, and why the straightest possible path across an ocean is worth hundreds of millions of dollars. Distance on the internet is not measured in kilometers. It's measured in milliseconds, and every millisecond has a price. Which brings us to the most remarkable part of this whole story. This planetary machine, the cables, the halls, the reactors, isn't serving some elite laboratory. It's serving you every day, and you never see it. Every morning before you finish breakfast, you've probably touched this machine a dozen times. Your phone synced overnight through a data center. The weather forecast was computed in one. The photo you backed up crossed a city on fiber and landed on 3 separate drives in case one fails. The AI that suggested a reply to your message ran for a few milliseconds on a GPU in a building you will never visit, possibly in another country. Its heat carried away by liquid, its power drawn from a grid being rebuilt to feed it. Billions of people do this every day. Each interaction is tiny. Together, they form one of the largest continuous flows of activity in human civilization. Trillions of requests per day, flowing through the same hidden system, sharing the same cables and the same halls, with a reliability so extreme we only notice it on the handful of minutes per year when it fails. We used to say the internet was a place. Then we said the cloud was a place. The truth is stranger. It's a single planet-sized machine, the largest machine ever built. And artificial intelligence is the most demanding tenant it has ever housed. So let's return, one final time, to our question. Where does AI actually live? Here is the answer this journey has given us. AI lives in a 100,000 GPU hall in the American heartland, roaring with fans, laced with liquid. It lives in glass threads under the Atlantic, flickering with laser light. It lives in a restarted nuclear reactor in Pennsylvania, in solar fields in the desert, in substations and switchyards and cooling loops. It lives 10 milliseconds away from almost every human on Earth. And that reveals something bigger. The AI boom is usually described as a software story. It isn't. Measured in concrete, steel, water, and watts, it may be the largest infrastructure project our species has ever attempted. Hundreds of billions of dollars a year on a pace that already rivals history's great build-outs, the railways, the interstate highways, the electrification of continents. Those took generations. This is happening in years. The chatbot window on your screen is just the doorway. Behind it stands a physical world most people will never see. Engineers threading fiber across ocean trenches, technicians tightening coolant fittings against 100-kilowatt racks, utilities restarting reactors, an entire civilization's worth of machinery hidden behind a single blinking cursor. In our next investigation, we'll follow this story one level deeper, into the data itself, where the knowledge inside AI actually comes from, who owns it, and what it costs to teach a machine everything humanity knows. Because that's the thing about the modern world. The most valuable things in it are almost never the things you can see. Hidden value is everywhere. You just have to know where to look.